So welcome back to the afternoon session. Now we have the pleasure to welcome Professor Rui Loja Fernandes from Illinois, Urbana-Champaign. He's going to talk about Bochner-Kähler structures after Robert Bryant.
Okay, thank you very much for the invitation. Being Portuguese, it's always a great pleasure to come to Brazil. So, as someone mentioned this morning, these were supposed to be more of a overview kind of talks. So what I'm going to try to do is a mixture of things. I'm going to try to tell you about some things that have been going on for the last 15, 20 years in some kind of extended Lie theory, but in a concrete application to classification problems in differential geometry of a certain kind. And so most of the time I'll be concentrating on the problem of classification Bochner-Kähler metrics to illustrate these points of view. But at some point things will become a little bit too complicated, so I will derive to other things. I should say that my job is a little bit complicated, because imagine that you've never heard about what is a Lie group or a Lie algebra, and you wanted to tell people about what is a Lie group and what is a Lie algebra and some results about them and some applications of them. So I'm kind of in a similar situation as that. All right, but let's give it a try. So basically this is based on some joint work with Ivan Strukiner, who is from here, from USP, and it builds on this paper of Bryant, where he classifies, in some sense, Bochner-Kähler metrics. So I already told you more or less what is my aim. There will be kind of 4 parts in this talk. So the first part, I will recall what is a Bochner-Kähler metric, and then I'll slowly build into the classifications and explain how these extended Lie theory enter into the picture. And the fourth part, I will come back to the classification issues. All right, so I start with a Kähler manifold. So my notation, I have a metric G, a complex structure J, and a symplectic form omega, and the curvature tensor R. And we form the usual quantities by taking traces. So we have the Ricci tensor, the holomorphic sectional curvature, the scalar curvature, and the traceless Ricci tensor. And because we are in the Kähler setup, things simplify a little bit by taking special orthonormal bases. Now, the curvature tensor has the usual symmetries, and besides, because we have the Kähler structure, it also has the symmetries relative to the complex structure. And if we pick all tensors that satisfies these symmetries, and we consider the action of UN on them, we can we get a representation of UN, which we can decompose into irreducible factors, and this gives us a decomposition of the curvature into 3 terms. So the first term there can be thought as, if you start with a Kähler metric and some scalar S, you can build a tensor out of them that will satisfy all those symmetries, and which is written there. So in the end, a metric which has R0 equal to 0 will be a scalar flat metric. And it will, a metric will have only R0 if it has constant holomorphic scalar curvature. So that gives you an idea of what that first term is. Now for the second term, you can actually pick this expression and start replacing one of the G's by a traceless symmetric tensor S, and we get a new expression that also satisfies those symmetries. And this expression has the particularity that its trace is this tensor S that we picked. And in the end, we'll see that for a Kähler metric, this R1 will be 0 precisely if the metric is Kähler Einstein. And finally, we have the last tensor. And the last tensor is simply subtract from R, R1 and R0 and R1. And so in the end, R0 represents basically the scalar curvature, R1 represents the traceless Ricci tensor, and the remaining part is called the Bochner tensor. So a Bochner-Kähler manifold will be one for which the Bochner tensor vanishes. And so that means the curvature is expressed, if you want, only in terms of the Ricci tensor. That's what the Bochner-Kähler metric is. All right. So examples of these are not that many. They were actually quite scarce, quite a few examples until this paper of Bryant appeared and clarify a bit the issue. So we have complex projective space with some constant holomorphic sectional curvature. We can take a product of two of them, provided we pick the sectional curvatures appropriately. If we take a locally symmetric space and we ask if it is a Bochner-Kähler, you'll see the only example is actually that, or, of course, open sets in there. So they are locally isomorphic to that. Or if we take Cn and we write the potential and we look for the condition on the potential for which the metric becomes Bochner-Kähler, then we get an ODE, which is written there for some constants A and K. And then you can try to find solutions of that ODE and produce some examples that are not very illuminating. And it turns out that up to scalar multiples, there is exactly one complete such example. And then there is also orbifold solutions, for example, weighted projective spaces. And that will actually turn out to be important later. All right. Now, so how does one find more examples? How does one find examples of these things? Well, there is the usual differential analysis that one can proceed and then try to somehow solve the equations. So let's go a little bit through that. So suppose I have my Bochner-Kähler manifold and I look at its unitary frame bundle. Then I have the connection one form for the Levi-Civita connection, and I have the tautological one form. Now, of course, these satisfy the usual structure equations, and they form a coframe on the unitary frame bundle. Now, in this, using the Bochner-Kähler condition, one sees that one can express the curvature in terms of some function that takes values in Hermitian symmetric matrices. So that's the expression of the curvature for some yet to be determined function S. All right? Now we can continue and we can, well, since d squared is 0, we can differentiate this equation, and that will amount to differentiate this, and there will be some derivatives of S. And if we do that, so the first thing that we obtain is that the differential of S is expressed in this way for some new function t, which now is a function that takes values in Cn. And now if we differentiate again, this function t has differential, an expression where it appears again a new function u, which now takes values in R. And finally, if we differentiate u, this thing closes, which is very nice. And in general, that will not happen. So that the word finite type that appear in the first slide has to do with that, has the fact that this has closed and stopped there. Okay? So these functions provide what's called a complete set of invariants. And let's put that aside for now. The point is that we have some equations that need to be satisfied. Right? So we have on the previous slide, the structure equations. And now we have these equations for these invariants, and any Bochner-Kähler manifold will have to satisfy these equations. So if I would like to find all possible Kähler structures metrics, what would I have to do? Well, I could start to look for a manifold P with a free action of UN, carrying some coframe, eta and eta, and some functions such that they would satisfy this system that we've just discussed. So that's it. That's what you have to do. Now, the point is, how do you do such a thing? How do you solve such a system? So, and of course the reason is if we do that, then this will be this P that we have here will be the unitary frame bundle of some Bochner-Kähler metric. All right? So the question is, how do we solve that? And so that's what I want to explain. So there is a way of looking at these kind of problems. Now, because this system is relatively complicated, and in order to explain all the theory and then explain you how to solve it and then come back to this will be a little bit too much. Here is another similar problem, which is kind of a toy problem. It's not a very serious problem, which is the following. So so now I ask for the following. I want to find all three manifolds P with a free action of SO2, a coframe, and some functions for which this kind of structure equations are satisfied. And it turns out that if you do that, then this P will be the orthogonal frame bundle of a surface with a metric G that satisfies this equation. So the Gaussian curvature has Hessian proportional to the metric. And this is an if and only if. So any surface has a metric which satisfies this equation, which we call a metric of Hessian type, will arise from solving this. So this is exactly the same flavor as before. We have to find a manifold with a free action, coframe, some functions satisfying this kind of system. All right? Okay. So these two problems and similar classification problems can be abstracted into a setup, which is the following. So one starts with what's called Cartan data. So one has a closed subgroup of GLN, G manifold X, and some equivariant maps C and R. So these are maps defined on X, this G manifold X, and which takes values in these two things, which is exactly well, let's move on and we'll come back to that. And an equivariant vector bundle map, which takes values in the tangent to my X, my manifold X. Now, when asked for the existence, so this is the data, and then one has to solve a problem. And the problem is this. I need to find a principal G bundle with a coframe and some equivariant map from this principal bundle back to X, for which these equations are satisfied. So you see here that what I did was I abstracted so in the previous two problems, this term did not appear because the connection was always the Levi-Civita connection, which has zero torsion. If you take a problem where the connections are not torsionless, then this term will appear. And then we have the curvature, and then we have these expressions for H. So what is H? Well, H is, in the previous slides, this set of invariants that we had in the case of Bochner-Kähler was this function ST and U. And so the two problems that I told you before is exactly this form. Right? So this abstracts what we had for Bochner-Kähler and what we had for these metrics of Hessian type. Okay? And so the question is, I give you this data, how do we solve, how do we show that some realization exists, or how do we find explicitly these realizations? All right, so if we do that, of course, then the quotient of my P by this action of G will be a manifold, and P will turn out to be the G structure over this. All right, so I was saying that if you solve this, then you get a G structure over the manifold P, over the manifold M, which is the quotient of P by the free action of G, which carries a connection and a tautological one form which satisfies these structural equations and which has this function F as the invariant. Okay? All right. But still, okay, I've just told you how to abstract the two problems into some abstract formulation. How do we actually find this principal G bundle P. Right? Now, this way of formulating the problem is a little bit annoying because we are looking for a manifold and a coframe, and these equations involve the things that we are looking for. So I'm going to twist this a little bit, and I'm going to take this data and I'm going to encode it in some different geometric way, which turned out to be useful. But before doing that, just to make sure that I don't lose you, so here is the data for the problems that I told you before. So in the case of the Bochner-Kähler, the X is the set of the possible set of values of these functions st and u. So this was a skew Hermitian. This took values in Cn. This took values in R. So that's the X. The G, of course, is un. It acts on X diagonally by acting by conjugation on the matrices and by the defining action on Cn, trivially on R. And then these are the expressions that you get from the equations that I wrote before for the R, for the F, and the C is 0 since there is no torsion. Okay, so it's some complicated things, some functions. And so the classification of Bochner-Kähler metrics amounts to the solving this Cartan realization problem. That's what I told you before. In the case of the metrics of Eschen type, the X will be R3, so the direct sum of SO2 with R2. The G, again, will act diagonally, acting trivially on SO2 and by the defining action on R2. And these are the expression for the curvature viewed in this way. It's just very simple in this case. And the function f is written there more or less explicitly. Okay. So this is much simpler than the other one, and that's the reason why I'm mentioning it, so that I can show you a couple of things later explicitly. All right. So the classification of surfaces of Eschen type, again, solving this Cartan realization problem. All right, so I told you that what we are going to do is going to turn this a little bit around, and we are going to encode this Cartan data in a geometric way. So here's what we do. So we build a vector bundle, which is just trivial as a bundle. It's just as fiber Rn plus the Lie algebra G. So in the case of Bochner-Kähler, this would be Cn plus Un, okay? And we built a bundle map from this bundle into the tangent to X, which puts together the function f that collects the invariant and the infinitesimal action of G on X. Remember, X comes with infinitesimal, with an action of the group G, so I take the infinitesimal version of it. The Lie algebra action is this psi. And besides this bundle map, there is a bracket where I put the torsion and the curvature. So this is a bracket on the sections. This is the expression for the bracket on constant sections. So I'm taking here U, if you want, a constant, so a vector in Rn, alpha, an element of G. And this means that because G is always contained, is a Lie algebra of endomorphisms, the group G was in GL, G is in Lie algebra of endomorphisms of Rn. So this is the action of an element of the Lie algebra on a vector V. I skew symmetrize. I have here the C that expresses the torsion. And here I have the Lie bracket on G and the curvature. Okay? And that gives me a skew symmetric bracket on the sections of this vector bundle A. It's only defined there on constant sections, but then I extend it to any sections by requiring a Leibniz type identity. So if I multiply a function by a section by a function, the function comes out, and then there is another term where the first section acts on the function by first turning that section into a vector field using this bundle map. So this uniquely determines a bracket on the space of sections. So that encodes the Cartan data. And then there was this realization of a Cartan data, this P coming with an action of G. So how do I encode that in this language? Well, that each realization, what it gives to me is a bundle map from the tangent bundle of P back to this trivial vector bundle A, which is given by this coframe, theta, eta, the coframe that was formed out of the connection 1 form and the tautological 1 form. And this covers the map H that I have from P to X, that it's part of, that it's the invariance in the end. Okay, so each realization is now encoded as such a bundle map. All right, so I put this data, I have encoded it, I have this realization, I think of it as such a bundle map. And the first thing that you note is that if you somehow know that there is a solution to the problem for any point in X, which means for any possible values of the invariant, then you check that this bracket that I defined, it's actually a Lie bracket. It satisfies the Jacobi identity. Okay? And that turns out to be quite important. And in fact, in all examples that I told you before, you can go there and check that the Lie bracket is satisfied. And in any relevant examples that you can find, the bracket will be a Lie bracket. So this Jacobi identity will be satisfied. So that is important because that will make this triple, this vector bundle, this bundle map, and this bracket, it's what's called a Lie algebroid, which I will tell you a little bit later more what it is. And so this algebroid encodes the Cartan problem. And the advantage of this point of view is that there is no more P in the picture. It's abstracted in this geometric object. So you don't have to think that these theta and these eta are one forms on some manifold that you are still looking for. Okay? So the Cartan data is encoded in this geometric way, and it makes perfect sense. But of course, if we want to solve the classification problem, we have to find this realization. So we have to find these bundle maps that appear here. I'm just translating things in some language. So I didn't solve anything. All right. Okay, so the other thing, of course, is, we don't want just to show that these things exist. We want to study their symmetries. We want to describe the moduli space of solutions. Is it smooth? Is it singular? And so on. And it turns out that this approach provides answers to all these questions. All right, so now in the end, I will want to explain how to solve this problem using these. So for that, I'm going to have to give you a small crash course on what are these extended Lie theory, these Lie algebroids, and their global versions, which are called Lie groupoids. So that's the next part of the lecture. So a small crash course on Lie algebroids and Lie groupoids. So first of all, what is a Lie algebroid? So it's a vector bundle. It comes with two things, a bracket on the sections, and a bundle map back to the tangent bundle to the base. And these are supposed to be compatible in the following sense. So this Leibniz identity that I wrote before holds. So if I take two sections and multiply one of them by a function, I can take it out at the expense of differentiating the function by this vector field obtained from the first section by applying the anchor. And then the Jacobi identity has to be satisfied, so this is indeed a Lie bracket. So there's a bit of repetition there. Now, very simple examples of these are the following. So, of course, if I take the tangent bundle to a manifold, that always gives me a Lie algebroid in a very trivial way. The sections of these are just vector fields, so I have the usual Lie bracket of vector fields. And the anchor in this case is the identity, and then you recognize these as a very simple identity for the ordinary Lie bracket of vector fields. This is one extreme. At the opposite extreme, I can take the base to be a point, and then all the differential geometry disappears, and what I have is just a Lie bracket on the vector space G. So I have a Lie algebra. So these are two extreme cases of this Lie algebroid. And a somewhat intermediate case is if you take an infinitesimal action of a Lie algebra on some manifold X, you can define an algebroid structure on the trivial bundle with fiber, the Lie algebra, by declaring that on constant sections, the bracket is just the bracket on G, and defining the anchor to be the infinitesimal action. Okay? So these are just very simple examples where you can use them as test cases for various things. So one simple thing is that these algebroids, they come with two things. They come with orbits, and that's because if you look at the image of this bundle map, you get a distribution in X. This distribution has varying rank, but still it's intervals, so it has leaves, and the leaves are called the orbits of A. And the other thing that also appears is if you look, instead of looking at the image, you look at the anchor, at the kernel of this map, the kernel of the anchor at the point, and the kernel, because of this property at the point, becomes a Lie algebra. So at each point you have a different Lie algebra, which is called the isotropy Lie algebra. And so if you go like to this infinitesimal action algebroid, you will see that these orbits are nothing but the orbits of the action, and the isotropies are nothing but the isotropies of the action. And that's the reason why I mentioned this elementary example. In the tangent bundle, there is only one orbit. There is the isotropy is trivial. In the case of Lie algebra, there is only one orbit, which is the point, and the isotropy is just the Lie algebra G. All right. Now, we are interested in more serious examples of algebroids. So here is the algebroid associated with the Bochner-Kähler metric. So the manifold where this algebroid lives is these manifolds where the invariants take values. The algebroid is the trivial bundle with fiber Cn plus Un. And then the Lie bracket on constant sections is given by this formula, which I gave you before. So here is the previous expression of the curvature, which I didn't even finish because it extends. And then there is the anchor map. So that's the type of algebroid that we are looking at when we are looking at this Cartan problem for Bochner-Kähler. And whenever I have a Bochner-Kähler manifold, the associated UN structure gives me this vector bundle map, which actually is more than just a vector bundle map, is a Lie algebroid map. So remember, I just told you the tangent bundle is a Lie algebroid, so I'm saying that this is a map from the tangent bundle algebroid to this algebroid, this Bochner-Kähler algebroid. And so somehow the problem is I have this A, which is given here, and I have to find these things. This is the problem. Okay? Okay, so to solve that problem, what we are going to do is we are going to make this thing into a global object. Okay, this thing is an infinitesimal object. We are going to make this into a global object. So what is the object corresponding to this Lie algebroid? Well, it has to be called a Lie groupoid, of course, right? So what is that? So, well, the most basic example to keep in mind is to think when you have a topological space and we look at paths, not loops, paths, modulo homotopy, right? So there is a homotopy, two paths which are homotopic, and there is a path which is not homotopic. And so what I'm saying is we look at paths, and I'm parameterizing paths by the interval 0, 1, fixing the parameterization. And I think of a homotopy class of such a path as an arrow that starts at the initial point of the path and at the final point of the path. And these things have some structure. So of course it has a source and a target map, which is just, to this arrow I have the source and the target. And I can compose them whenever two such things match. And the point is that if I take paths and I concatenate them, the homotopy class of the concatenation only depends on the homotopy classes of the paths I started with. So this is a well-defined operation on the set of homotopy classes of paths. Furthermore, for each point of my topological space X, I have the trivial constant path based at that point, and so that gives me what's called an identity arrow at X. So X is somehow embedded into this space of paths through this identity map. And it is an identity map in the sense that under the previous multiplication, if I compose with an identity, I don't do anything, right? And there is also an inverse, which is just I take a path and I take the opposite path by running the parameterization in the opposite way. And clearly, if I compose two such things, what I get is the identities either at the source or at the target. Okay? So this is an example of a simple example of a groupoid, and it turns out that this space is more than just a space. It has a natural topology. So this is a topological space. And then source, target, multiplication, and inverse are all continuous maps. So this is an example of a topological groupoid. If you require not just to have a topological space, but a manifold, then this thing is also a manifold of twice the dimension of X. And these maps, they all become smooth maps. The target and the source become submersion. The inversion becomes a diffeomorphism, and so on. And the unit is an embedding. So this thing, this space of paths on this manifold model of homotopy, is an example of a Lie groupoid in the smooth category. So in general, a Lie groupoid is just two manifolds with a pair of maps, a pair of submersions, the source and the target. And we have a partial composition. So in the sense that if I have two arrows, I will compose them if they match. And the composition gives me some product. There is some identity for each point in X, which has the identity property. And there is an inverse, which has the inverse property. Okay. So here are some very simple examples of Lie groupoids. So I just gave you one, which was this fundamental groupoid of a manifold. Is another one. If I take just a pair groupoid and I think of a pair of points as just an arrow from the first element in the pair to the second element in the pair. There is an obvious composition. And that's an example of a Lie groupoid. In some sense, is an X. So I was saying that if X is just a point, then this notion just becomes the usual notion of a Lie group. And if I have an action of a group on a manifold, I can make that into a groupoid, called the action groupoid, because I can think of such a pair as an arrow. So if I have a pair given by an element, so the product will be an arrow which has source, the source of tau, and target, the target of gamma. So it will lie there on the intersection of the source and target. This picture is a bit misleading because these things don't have to intersect transversally or anything. They could be equal, for example. All right, but now I'm saying that we have these algebra associated with it. So the vector bundle is going to be taking the tangent to the source fibers along the identity section. So I took the tangent to the green things along X. And that forms a vector bundle over X. So that's the algebroid. And then I have this bundle map from A to Tx, so the anchor. Well, I used here the source, so now I use the target. I take the differential, and I restrict to these, and I will get a bundle map from these back to Tx. So that's my anchor. And finally, I have the Lie bracket, and that should follow more or less the same construction as in a Lie group. So the first thing to realize is that sections of this thing, so let's see, that was the anchor. And now, to define the bracket, let's look at sections of A. Well, if I have a vector tangent at one fiber, and I do right translation by tau, I will get a vector tangent to the green, to the source fiber, but at that point. But now if I start varying my tau, I will get a bunch of tangent vectors along these blue tangent to the green lines. And that was from a single vector. So from a single vector, I got all those tangent vectors along these green lines. So if instead of taking a single vector, I take a vector at each point of X, so a section of A, and I do right translations, this will propagate to a vector field on my G, on the total space of my groupoid, which is tangent to the green lines, and which is right invariant, because I use these right translations to build it. So a section of A gives rise to such a right invariant vector field, and the converse is also true. If I start with the right invariant vector fields, I can restrict it along X, and that gives me a section of A, and this is a bijection. So there is an identification between sections of A and right invariant vector fields on G. Therefore, I can define the bracket of two sections by extending them to right invariant vector fields, take the usual bracket, and then restrict to the identity section. And that defines a Lie bracket on the sections. And you can check that, so that's a Lie bracket because we had a Lie bracket on vector fields. And you can check the Leibniz identity for this map rho by using some standard property of Lie brackets. So that's how you build out of a groupoid, how you build the algebroid. Well, now you can go to these very basic examples and check what is the algebroid, say, of the fundamental groupoid. And the answer is, what is the algebroid of the fundamental groupoid? For no one. There are some people in the audience who work in the subject, they know the answer. It's just the tangent bundle to X. So the fundamental groupoid integrates the tangent bundle to X. Now the pair groupoid that I also had before there also has algebroid the tangent bundle to X. But that's just the usual thing that if I have a Lie algebra, there can be several Lie groups integrating them, right? Also for the action groupoid, or for a Lie group, I recover the usual construction of the Lie algebra out of a Lie group, and for the action groupoid, I will get the action algebroid that I wrote before. Okay? All right. Okay. Oh. So now you can ask if these basic theorems of Lie theory that we study when we do a course in Lie theory, if they hold. And the story starts nicely. So Lie's first theorem, if I have a source-connected Lie groupoid G. So here, what in the Lie theory, you typically require the group to be connected or to be simply connected. That's replaced here by the source fibers being connected or the source fibers being simply connected. Okay? It doesn't matter if you take source or target because they are diffeomorphic via inversion. But so given a source-connected Lie groupoid, there is a unique source-simply connected Lie groupoid, which has the same Lie algebroid, and which is a covering of the groupoid you started with. Okay? Just like for Lie groups. Given a Lie group, there is a unique connected Lie group, there is a unique simply connected Lie group covering it with the same Lie algebra. For Lie's second theorem is the integration of morphism. So I didn't say what is a morphism of Lie algebroids. You can try to guess what it is. But so if I start with a Lie groupoid G1, a Lie groupoid G2, with algebroid A1 and A2, and I assume the first one is source simply connected, then any algebroid morphism from A1 to A2 integrates to a unique groupoid morphism from G1 and G2. Okay? So Lie's second theorem also goes through nicely. And the problem, and what makes actually the theory interesting, is that Lie's first theorem is not true. It's not true that every Lie algebroid comes from a Lie groupoid. So that was a problem that was open for many years, and then eventually it was solved. And nowadays, we understand completely the obstructions to integrate an algebroid to a groupoid. So there is a way to decide, if I give you an algebroid, whether it comes from a groupoid or not. All right. Can anyone see this? No, right? Doesn't matter. You know what is a Morey-Cartan form on a Lie group, right? It's a G-valued one form, which is right invariant, left invariant, whatever convention you take. So what I'm writing there is that there is, on a groupoid, there is a Morey-Cartan one form. And it's just given by the same formula. But now it's just a little bit more complicated because the problem is that you want to use right translations. Right translations are not always defined. So this Morey-Cartan form doesn't apply to any tangent vector to the groupoid. It only applies to vectors that are tangent to the source fibers. But so there is a notion of a Morey-Cartan form. So it's a source-foliated one form with values in the Lie algebroid. It's just the analog for a Lie group. Okay, this I hope people can see a little bit better. So what is the point of this result? Suppose that our algebroid is trivial as a vector bundle. And remember, those are the kind of algebroids that appear in connection with those classification problems. They were always trivial as vector bundles. And that's an important thing. Then what I say is that if I have some groupoid integrating this algebroid, and I restrict the Moret-Cartan form to a single source fiber, what that gives me is a Lie algebroid map from the tangent of that source fiber to A that covers the target map. So this should remind you of this realization as a vector bundle map, which comes with some coframe and some map to the algebra. And moreover, these things, they are universal. These morphisms, they are universal. In what sense? In the sense that if I start with a manifold with a coframe, which induces an algebroid map from the tangent bundle to A, it is basically of this form. So it's locally isomorphic to this. So these are universal. Okay? So this means that if you are interested in finding coframes that have this property that map to this A, you can find them by finding integrations of A and finding source fibers with the restriction of the Moret-Cartan 1 form. And that's the basic idea behind how to solve this Cartan problem. All right, but now let's go back to G structures. So this thing that I just told you was about coframes. And when we have G structures, our coframes are a bit special because they were made out of a connection 1 form and this tautological 1 form, right? So they're just not arbitrary coframes. So these algebroids associated with G structures, they have a bit more structure that one has to use. And so really the thing that you have to keep in mind is that this coframe has this special form that I just told you. It's made out of a connection 1 form and this tautological 1 form. Now, from now on, just to make things a little bit, to tell you true statements, I will assume G compact. But that's not really very, very important. So, back to our Cartan data. So I told you Cartan data can be encoded as these bundles. So here is what I told you before, except that now you know what is an algebroid. And so I have abstracted this to a definition. So a Lie G algebroid is just an algebroid whose trivial as a vector bundle. The fiber is Rn plus some Lie algebra G, plus the Lie algebra G. G is the fixed group. Note that X is a G manifold. And this algebroid has an anchor which is given by an equivariant map plus the infinitesimal action associated with these G manifolds. And the bracket on constant section has to take this special form for some G equivariant maps C and R, right? And now I don't even need to assume that this was coming from some G structure as I did before. I can just make this as a definition. Anyway, and then I will say that the G realization is just a manifold with a locally free proper G action together with an equivariant Lie algebroid map to A. And that map will necessarily be of this form where this is a coframe. So back to our problem. The problem is really, I gave you this A, I have to find these G realizations. But now I know from what I told you just one slide before that you can do that by looking at integrations of A, taking source fibers and restricting the Moret-Cartan 1 form. So to do that in this scenario, we have to be a little bit more careful because we want these things to come with an action of G. So we don't want just to have some manifold with some algebroid map to A. We want that this thing comes with a Lie algebra, with a Lie group action. So if I start with such a Lie groupoid, we have automatically, from its definition, this inclusion of the action group, the infinitesimal action algebroid on A, which is just taking an element in the Lie algebra, including the factor. Remember, A was the trivial vector bundle Rn plus G. So I'm just taking the part in G. That turns out is just an injective Lie algebroid morphism. And so what really we need is what we call a Lie G groupoid, which is just a groupoid whose algebroid is a Lie G algebroid, and for which we have a groupoid morphism from the action groupoid of G on X into my groupoid G, which integrates this map. Okay? So again, this is because I want to get the solutions manifolds with actions of G. So in fact, if we look at this morphism, it defines a G action on G by simply, so if I take an element here, gamma cross G, this is switch, this should be G cross gamma, whatever. And if I include it in G, I get an arrow. And then I can take right translation or left translation by that arrow. And that gives me a right G action on G. And this right G action has the following properties. It makes the target a G invariant map. It acts along the source fibers. So each source fiber becomes a G manifold. And it is proper because I'm assuming G compact. And it's locally free because this thing was injective. So in particular, if I look at the source fiber of such a Lie G groupoid, it's a principal G bundle over this quotient, which is now an orbifold because the action is only locally free. So somehow, if I start with a Lie algebroid, I integrate to a Lie G groupoid, I will get these orbifolds solutions somehow. So here is the basic theorem that allows to solve these classification problems. So if I start with a Lie G groupoid integrating a Lie G algebroid, each source fiber equipped with the restriction of the Moret-Cartan one form gives me a solution. So it gives me a manifold with an action of G, which becomes a G structure over the quotient, over the orbifold. And that satisfies my structure equations that define my Lie G algebroid. And this thing is universal in the sense that any solution is going to be isomorphic to one such solution, at least up to cover. So you are guaranteed that all solutions will appear in this way somehow. So if you go back now to the Bochner-Kähler situation, here is what you conclude. Because the algebroid that you have there, it is indeed an algebroid. It satisfies the Jacobi identity. For any value that you pick of these invariants S, T, and U, you are guaranteed that there will exist a Bochner-Kähler orbifold which satisfies the equations and which takes this value at some point. Okay? Now, there is something going on here because I assumed here that there was a Lie G groupoid integrating this Lie algebroid. So I'm cheating a little bit. So here is the cheating that it's going on. First, I actually don't need to integrate the algebroid to the groupoid. I only need to restrict the algebroid to an orbit and then integrate the restriction to an orbit. The second thing is I don't really need to find global integrations. I don't need to really find Lie groupoids. I only need to find local Lie groupoids, whatever that means. So there is some cheating going on, but basically the idea is that. So there is some technicalities involved. In any way, that can be used to prove this corollary. Now, a couple of remarks. So usually we are interested in solutions that may have special properties. So for example, we like to have complete solutions. Now, to use this formalism to find complete solutions, it depends really not just having local G integrations, but in having G integrations. And that doesn't happen always. But still, we can decide by looking at A, whether that happens or not. So there is an obstruction theory that builds on this obstruction theory that I told you that was used to solve Lee's third theorem for algebroids. There is an obstruction theory that it's more refined, that it's for these Lie G algebroids, that allow us to understand whether there are or not G integrations, and therefore whether there are or not complete solutions. So complete Bochner-Kähler metrics in that case. Of course, if you don't integrate, you will never find explicit solutions. If you really want to find explicit solutions, you have to find explicit integrations. Now, I'm not claiming that that's easy. However, it turns out that in the case of the Bochner-Kähler metrics, it is possible to find global integrations. But that's a different story, okay? And, I mean, in the end, of course, I mean, this has nothing to do with the specific situation of Bochner-Kähler. So if I looked at these metrics of Hessian type, the same story that I just said holds, okay? For each values of the invariance, there is a solution, a germ of a solution if you want, and you can decide whether there are global complete solutions or not. So let's look at it. So here is remember the original problem for metrics of Hessian type is you have a surface and you have a metric whose Gaussian curvature satisfies this equation. And so making the differential analysis, the structure equations that you get are these. So K1 and K2 are the principal curvatures. And I'm using the same notation. So theta is the tautological one form, eta is the connection one form. And so here the curvature appears there. And now we make this into these Lie G algebroids. Remember, that was just a different way of encoding the structure equations. So there is the bracket, and here is the anchor. Okay, so there are three invariants. The bases are 3. The fiber is SO2 plus R2. And so the fiber is also R3, and these give you the bracket, and these give you the anchor. It's a pretty straightforward thing. Okay? So now what we have to do to find these surfaces, we have to integrate this thing. Okay? Or at least decide if it has integrations or not, and so on. So, as I said, you don't really have to integrate the whole thing. You have to look at the orbits and ask yourself if the restriction to an orbit is integrable. So maybe I should have mentioned that before. It's very possible that an algebroid has a restriction to every orbit integrable and not being integrable. Okay? Anyway, so in this case, it's very easy to understand, and that's why I chose this as an illustration. So the orbit foliation of this algebroid is given by the level sets of this function. So here is a picture. So in this picture, I have K1, K2, and I shifted the curvature by 1. And so the level sets of these are described here. So we have these spheres, and then we have these surfaces of revolution. And what do we see? So there are 2 points here, which is this point and this point, which are points where the anchor is 0. So these are orbits of dimension 0. Now, if you have an orbit of dimension 0 and you go through the theory, what that means is that the source fiber at that point is just a Lie group. So the restriction of the algebra to that point is obviously integral. It's just a Lie algebra, and you just get a Lie group. And so these things correspond to solutions whose principal bundle is a Lie group. Okay? And so what are those? Well, one is going to be a metric of constant curvature, positive constant curvature, and the other one is going to be a metric of negative constant curvature. Okay? So those are those 2 points. And now you have to analyze what happens with the other leaves. So it turns out from this obstruction theory that if the leaves have trivial pi2, there is no problem. The thing is always integrable. So that's an example of how powerful the obstruction theory is. You don't have to do anything. Just have to look at pi2 of the leaf. Is trivial? Fine. Don't have to worry. So you are guaranteed that over these, for these values, there will be solutions, and there will be complete solutions, at least orbifold solutions. Okay? Now you can discuss whether they are smooth or orbifold, but at least there will be orbifold solutions. For the spheres, the pi2 is not trivial, and you have to compute the obstructions. So there is a recipe to compute the obstructions, and the obstructions tell you that not every sphere is actually integrable. It will oscillate by spheres, and it's a behavior like rational, irrational. So there will be like rational spheres where the thing is integrable, and irrational spheres where the thing is not integrable. Okay? And so you know that for points in this region, there will be matrices of Hessian type if you are in good spheres, and there will be metrics of, there won't exist any metrics of Hessian types if you are in bad spheres. Okay? And then there are two surfaces here, limit surfaces, which also don't have pi2, so the analysis, it's also okay, there is no problem. Now, what I'm not going to explain, because that would be really like at least another lecture, is doing this analysis for the Bochner-Kähler example, because the algebra is complicated, and then you have to understand these foliations of the algebroid. You have to go through the analysis to see what happens for each leaf and so on. But what I'm telling you is that this can be done. Okay, and you recover. So this paper of Bryant that I mentioned at the beginning has, I don't know, 120 pages, and most of the things that he does is done in a quite ad hoc way, with some ad hoc arguments. And by using this formalism, you can reduce this from 120 pages to maybe 15 or 20 pages. Okay? And you can actually improve them. So why can you improve them? Well, you can improve them because you can decide explicitly for which things exist or don't exist. That's one thing. The other thing you can improve, and it's a story that I didn't tell you about, so I didn't tell you about symmetries, and you can use this algebroid to detect what are exactly the symmetries of the solutions. But you can also use this algebroid and this groupoid formalism to understand the moduli space of solutions, to understand if the moduli space is singular or not, and if it's singular, what kind of singularities it has. Okay? And so you can do all that in a systematic way using this formalism. All right. Just some closing. Am I okay with that? I'm running. I'm over time, right? All right, so this is the last slide. So this was just a comment that I just made. I told you that at some point I assumed G compact. Really what's important is that the kind of families of G structures that you are dealing is what's called G structures of finite type. So after some prolongation, the thing stops. And so the analysis is more or less similar, but a bit more complicated because you have to work on these prolongations. And just to close with an open problem, in many examples, including the case of Bochner-Kähler, another example you can treat with this formalism is symplectic connections with special holonomy. The algebroids that appear there, they are related with another geometry which is called Poisson geometry. So they are cotangent bundles of Poisson manifolds, whatever that means. And because of that, symplectic geometry comes into the picture. And I don't understand, and it's an open problem to understand why that is the case, why these algebroids come from these things. And I'm really curious to know what's the answer to that question. It should clarify quite a few things. Okay, thank you.
Are there any questions? Yeah.
Can you talk a bit about this very last point? Well, you mentioned there are algebras related to the issue of connections with special holonomy. Can you expand a bit on how this goes?
Symplectic connections with special holonomy, they be treated by... Sorry. Symplectic connection and special holonomy, they were discussed by Merkulov and Schwarzhofer in the early 2000s. And they basically have a classification into 4 different types. One of the types turns out to be Bochner-Kähler. And they also discuss, they go also through a classification similar to what Bryant does in his paper, again using some ad hoc methods. But already there they mentioned that the solutions can be found by using what's called some symplectic realizations of Poisson manifolds. So by finding some symplectic manifolds that somehow desingularize Poisson manifolds. Now, what is really happening is that underneath the algebroid that describes that classification problem, this kind of Lie G algebroid that I told you about, those are the cotangent bundles, or more precise, they are obtained from the cotangent bundle of a Poisson manifold. The cotangent bundle of a Poisson manifold has a canonical Lie algebroid structure. And in those examples, they are all obtained from some restriction procedure from such an Lie algebroid. And because of that, when these algebroids that come from Poisson manifolds, they integrate to groupoids which are symplectic groupoids. The groupoids have a symplectic structure. And that symplectic structure plays a role in, for example, in describing the moduli space of solutions and so on. Okay. But it's not at all clear why that is the case. It's just like, oh, here is the structure equations. Here is the associated algebra. Oh, it comes from a Poisson manifold. Why? And this Poisson manifold, I mean, it's a long story. This Poisson manifold comes from 2 gradable Lie algebras and whatever.
Any other questions? Okay, thank you.